This educational video brought to you by the Society of Mechanical Ventilation. Basics of Mechanical Ventilation, Part 1. Our objectives are to define the breath variables, describe some of the curves available during mechanical ventilation, and explain briefly some of the basics of the respiratory mechanics. Talking about the difference between a normal breath, like a negative pressure breathing, versus a positive pressure breathing during mechanical ventilation. The figures on the left side here, patient breathing normal breathing, the atmospheric pressure 760 millimeter mercury. This is the airway pressure, alveoli with the alveolar pressure inside, chest wall, diaphragm, and the abdomen. With the diaphragm going down during inspiration, creates a negative pleural pressure, so the air rushes in and the chest wall expands. Opposite in positive pressure ventilation, the ventilator pushes with an airway pressure, in this example 40 centimeter water, equivalent to 790 millimeter mercury. The alveolar pressure becomes positive relative to the atmospheric pressure, and the pleural pressure also becomes positive. And that gets us the transpulmonary pressure, which is the difference between the alveolar pressure and the pleural pressure. Describe the breath during mechanical ventilation. The breath is divided into two parts, inspiration and expiration. When we describe the breath, there is three things to talk about. The trigger, what starts the breath, the limit, what continues the breath or the maximum, and what cycle, what ends the breath. Here we'll talk about the trigger. This is a pressure controlled mode. Patient is passive, and here patient is active, has effort, and this is volume control, patient with no effort, and patient has very high effort. Trigger could be one of two things, either machine triggered or time triggered, and that's if the patient has no effort or unable to trigger the ventilator, and it will be set respiratory rate for the most part. So if the set respiratory rate is 15, the patient will be getting a breath every 4 seconds. Patient triggered is usually either flow or pressure or other triggers like patient electrical diaphragmatic activity in some of the modes, or a combination of modes of both. Variable of the breath is the limit, which is usually the maximum value allowed during inspiration, that orange arrow. So in pressure controlled modes, it's usually the pressure, and other modes like volume controlled, it's usually the flow. We'll talk about those in specific when we talk about each modes. Variable is what terminates inspiration to start in the expiratory phase, which is that green arrow. And again, depending on the mode used, like in pressure controlled modes, it will be time. After the inspiration had a certain inspiratory time, it will cycle and exhalation starts, or flow, and in some volume control and pressure support modes. Again, we'll discuss those when we speak about each mode separately. One important aspect of mechanical ventilation is monitoring, and new generation ventilators gives us lots of curves, either against time or against each other in the form of loops. So in this example, we're going to talk about the pressure curve, flow curves, volume curves against time. So in this upper panel here is the airway pressure in centimeter water on the y-axis and time on the x-axis. The purple curves here are the flow versus time, and on the bottom the green is the tidal volume versus time. So the ventilator applies the force in the form of positive pressure or the driving pressure to the patient's airways to generate a tidal volume or volume of gas entering the lungs. Now, different ventilator modes would use one of 5 different flow deliveries, and depending on the different way the ventilator applies the gas, which is the flow, the configuration of the airway pressure, as you can notice here, and the tidal volume will vary. There's basically 5 different flow curves used. This is the constant or square flow waves used in volume controlled modes, the descending flow curve, mostly in pressure controlled modes, but also can be used in volume controlled modes, the sine flow wave, which is not being used, the decelerating flow waves, and this mostly in pressure controlled modes, and the ascending flow curves, which also pretty much obsolete. So it's important to know that the ventilator does not have a spirometry to measure the tidal volume, but it calculates the tidal volume by integrating the flow curves over the time. One of the common loops is the flow volume curve or flow volume loop. So the flow volume loop shows the flow on the y-axis and the tidal volume on the x-axis. You can see the top part is inspiration and the bottom part, the negative flow, is expiration or exhalation. That's how the breath is going. And in this example, we're using a loop from a volume controlled mode using this constant or the square flow wave curve. If you notice during exhalation, it's very nice and straight and goes back to the baseline before the next breath starts. That's a normal patient. In this B curve, you can notice how the expiratory flow is very deep. In this example, it's reaching almost minus 130 versus a normal person here was minus 40. And it goes very quickly and steep. That's a patient with ARDS or restrictive lung disease with low compliance. In this example here, that's a patient with an obstructive airway disease or COPD. And again, you can notice the expiratory flow is very low and the expiratory decay goes very slow and the breath ends here, not reaching the zero, creating what we call auto PEEP, which we'll be talking about in the next slides. Another very important curve or loop, it's called the pressure volume curve. And we will talk about this in another lecture when we speak about setting PEEP. But the pressure volume curve shows the airway pressure here at the bottom on the x-axis against the tidal volume on the y-axis. Once we increase the airway pressure, you'll notice that the tidal volume start to go inside the lung. So this is the inspiratory limb and this is the expiratory limb. And to get this curve accurate, quasi-static curve, you have to have a passive patient with no effort to get an accurate curve, which gives you more information about the compliance of the respiratory system. It has to be done with a very, very slow flow, so the effect of resistance becomes minimum, and it has to be used using the constant square flow waveform. So in this example, this is a normal lung or respiratory system. As the airway pressure is increasing, the tidal volume is going up and going down. If you can notice, both are pretty linear curves because of the normal compliance. and the difference between them is something we call the hysteresis. In slide B, this is an ARDS, or severely restrictive lung disease. You can appreciate the difference here. The airway pressure is increasing with no much increase in the tidal volume until that point, which is called the low inflection point. Inspiration becomes linear or more compliant. So this is the more compliant part of the respiratory system, and this is very low compliance. And again, to reach a point where after that adding more pressure does not give you much tidal volume. So again, low compliant area. And during exhalation, you can notice that the tidal volume is maintained until a point where the tidal volume starts dropping, which usually termed the point of maximum curvature. Patient C here is a patient with severe obstructive lung disease, or COPD. Again, you can appreciate the airway pressure as much going up, and the tidal volume goes very high. And again, there's some hysteresis, but definitely less than the one in restrictive lung disease. Important equations during mechanical ventilation is one of them is the equation of motion, and this equation describes the force needed to drive the gas into the lungs, and that's derived from the Newton's law of motion. And what that equation states is that the pressure total is a combination usually between the ventilator, which is a P vent, plus the patient, which is a P mus or P muscle. Of course, if the patient is paralyzed or with no effort, it will be only the work of the ventilator. And the obstacles it has to overcome are the tidal volume over the respiratory system compliance, plus the airway resistance multiplied by the flow, plus the total PEEP, whether it's the applied PEEP plus the intrinsic PEEP. And this comes very important when you assess the patient work and calculating the respiratory mechanics. So respiratory mechanics, and when we talk about those, are usually the compliance and or elastance, airway resistance, and O2 PEEP. So let's start by the compliance and elastance, and they are basically inverse of each other. So compliance is 1 over elastance, and elastance is 1 over compliance. What that means is describe the relation of the respiratory system, which is a combination between the lungs and the chest wall, including the abdominal wall, how it behaves in terms of the applied pressure exerted on it. Simply, it's the relationship of the tidal volume divided by the pressure. So the total respiratory system compliance equal tidal volume over plateau pressure minus total PEEP. And to get those numbers, you have to look at the figures here on the left. This is a patient on pressure controlled ventilation, and this is a patient on volume controlled ventilation. And if you can notice the difference in pressure controlled, basically there's no peak and plateau, it's only one pressure. So that's inspiration and exhalation, which is C. And the flow, the peak inspiratory flow, peak expiratory flow, and the tidal volume. To get an accurate measurements or static measurements of the compliance or elastance, classically it's been described using the volume controlled mode with the square or the constant flow. You have to apply an inspiratory pause. So what happens is at the end of the breath, point A here, that's a peak inspiratory pressure. You put the pause, and point B is the plateau pressure. And the calculation will be the tidal volume over the plateau pressure minus the total PEEP. And the reason you have to also do an expiratory pause maneuver to calculate the total PEEP, as we will talk about. Dig deeper a little bit in the compliance, and can we differentiate between the lung compliance versus the chest wall compliance? In the last slide, we calculated the total respiratory system compliance. And the answer is yes. What we need is esophageal balloon manometry, basically to estimate the pleural pressure, and we'll talk about how to do it. So in this example, number A is the airway pressure. Notice again that the patient is on a volume controlled mode with the constant or square flow. Number B here, we put an esophageal balloon manometry, and you can see it here. All those bumps are like artifacts from the heart. And number C, we were able to calculate the transpulmonary pressure we talked about earlier, which is simply the airway pressure minus the esophageal pressure, gives us transpulmonary pressure. Number D is the flow, as we talked about, again, inspiratory, expiratory flow, and number E is the tidal volume. So you would notice that we put an inspiratory pause here. We have the peak inspiratory flow, or here. In this example, it's 31 centimeter water. We put an inspiratory pause and we got a plateau pressure of 27 centimeter water, and the PEEP, total PEEP, is 15. And if you notice here, there's an expiratory pause, so the total PEEP is 15. And the esophageal pressure with the same maneuvers, end inspiratory esophageal pressure about 17. The end expiratory esophageal pressure, that red dots, is 12. And the peak esophageal pressure is 18. In the transpulmonary pressure, the end inspiratory transpulmonary pressure, again that white line, is 10. So this 27 minus 17 equal 10. End expiratory transpulmonary pressure is 3 here, which again this minus this. And the peak inspiratory transpulmonary pressure is 13, which is the green dots here. Again, the peak minus the peak. The peak inspiratory flow in this example is 45 liters per minute, and the tidal volume was 500. So let's see the calculations. So to calculate the total respiratory compliance, as we talked in the last slide, tidal volume, which is the 500, divided by plateau airway pressure minus total PEEP, so 27 minus the total PEEP, we said 15, comes to 41.6 milliliter per centimeter water. How about the chest wall compliance? Very similar, but it will be the difference. It's the tidal volume over the end inspiratory esophageal pressure, which is here the white line, 17, minus the end expiratory esophageal pressure, which is here the red dots, which is 12. So 500 over 5 comes to 100 millimeter per centimeter water. How about the lung compliance? Very similar, but the difference will be the denominator here. So tidal volume divided by end inspiratory transpulmonary pressure, which the white line here, it's 10, minus end expiratory transpulmonary pressure, in this example is 3. So 500 divided by 7 equals 71. Little complicated, but very important to differentiate between, is it chest wall compliance or a lung compliance. Airway resistance is simply difference of pressure between one point to the other point divided by flow, like in that water pipe from point A to point B, divided by how fast the water is going, which is the flow. Same in mechanical ventilation, back to the same figure here with the volume controlled ventilation and the constant or square wave form. We put in inspiratory pause here. So if you notice, the airway pressure goes up, peak inspiratory pressure, we put the pause. The pause has to be long enough. This is short a little bit. It has to be at least 3 seconds. And you notice the drop, and that drop because there is no flow, so there is no resistance. So the equation will be peak inspiratory pressure minus plateau pressure, which is point A to point B, divided by the flow. Inspiratory flow in this example is 40. Notice that the airway resistance is in centimeter water per liter per second, but the flow of the ventilator is giving us liter per minute. So it will be 20 minus 15 divided by 40, but we have to divide it again by 60 to get it liter per second. So 5 divided by 0.66, in this example the total resistance is 7.5 centimeter water per liter per second. And of course we all know that the resistance encompasses both the anatomical airway resistance plus the artificial airway resistance and the friction forces, which we usually ignore. And the factors influencing resistance are most important is the radius and the length of the tubes per Ohm's law. Back to that busy graph, similar to the compliance, but this time we're going to differentiate between long resistance versus chest wall resistance. And the honesty is this is not as important as the compliance because the chest wall resistance is usually minimum, and most of the airway resistance usually coming from the lung, again the anatomical airways and the artificial airways. So let's go back to that example, the calculations. Total respiratory resistance will be the peak inspiratory pressure, in that example 31, minus the plateau pressure, in that example is 27, over the flow, which is 45 liters per minute. So it will be 31 minus 27 over 45 divided by 60. So 4 divided by 0.75, total resistance 5.3. Chest wall resistance will be the peak esophageal pressure, in this example 18 here, here 18 minus the end inspiratory esophageal pressure, the white line, in this example 17, divided by the flow, same flow, so it will be 1.3 centimeter water per liter per second. Lung resistance will be peak transpulmonary pressure, which is the green line here, 13 minus the end inspiratory plateau transpulmonary pressure, which is that white line here, 10. So 13 minus 10 over the same flow, it will be 4 centimeter water per liter per second. Time constant is another important and very interesting phenomena, actually borrowed from electrical engineering and physics. What time constant is, it's the amount of time taken by the lung unit to fill during inhalation or empty during exhalation at a stable pressure. This parameter is measured in seconds and is a product of both compliance and resistance. So it basically gives us overall characteristics of the respiratory mechanics. To be noted that one time constant is necessary to defined as to fill or empty 63% of the lungs, and usually takes about 4 to 5 times constants to fully inflate or empty the lung units. Of course, our lung units are very heterogeneous. Some alveoli has longer and some other has shorter time constants, but this gives us an idea of the whole respiratory system. So this is an example of a patient on pressure control ventilation mode with the decelerating waveform of the flow. Number A is a normal lung, and you can see here the peak inspiratory flow. The first blue arrow is the first time constant, second blue arrow second, and the third. And you can notice that the inspiratory flow did not reach the baseline 0 here. So it's not totally inflated. And if you want to increase the tidal volume, you increase the inspiratory time to get the flow down here. You'll get more tidal volume. Exhalation, again, you can see peak expiratory flow. This is down here, decayed 63%, another 63%. So in this example, 4 time constant to reach down the baseline. The patient in the middle here is with restrictive lung disease, and of course you can notice how the inspiratory flows very high and goes down very fast because of the very low time constant. Same with exhalation. The lung closed very fast because of the restrictive nature and the short time constant, versus that patient on the right side was obstructive airway disease or COPD, and you can see the very slow inspiration, filling of the lungs. Here, for in this example, only stopped at 2 time constant, same with exhalation, 2 time constant, and that resulted in O2 PEEP. The flow, expiratory flow did not reach the baseline, and that is O2 PEEP. We're coming to our last slide here, and it's a very important slide and oftenly missed, the phenomena of O2 PEEP or intrinsic PEEP. As we know, PEEP is a positive end expiratory pressure here. O2 PEEP or intrinsic PEEP meaning additional PEEP that is remaining at the lung in the alveoli at the end of exhalation before the next breath start. Problem is most of ventilators does not tell you exactly how much O2 PEEP, although some new ventilators calculate it. But you're not gonna see this waveform here. What we have to do is put a maneuver called end expiratory maneuver. Most of the time by vision, this is again a patient on pressure controlled ventilation with descending airways flow, and you can tell the lung did not, inspiration flow did not go to the baseline. Same, the expiratory flow did not reach. So this is O2 PEEP. How much is the O2 PEEP? We have to apply end expiratory pause maneuver, and you will notice that the airway pressure will go from here to here. So that big arrow, that's the total PEEP. So for example, if the total PEEP here is 10 and the applied PEEP is 5, so the intrinsic PEEP is 5. And O2 PEEP is very important because it can affect hemodynamics, can cause a lot of dyssynchronies and high patient effort and failure to trigger. So it has to be corrected, noted and corrected. How do we correct it? A lot of ways. Most importantly is to try to decrease the respiratory rate and the tidal volume, which is the minute ventilation. You can try to prolong the exhalation phase, expiratory time. Some people apply about 75 to 80% of the total PEEP. Some other people disconnect the ventilator and push on the chest to get the O2 PEEP out. I really do not recommend that unless it's a dire situation or causing severe hemodynamic collapse, because it can cause lung de-recruitment. Some easy references to read written by our group. You might find it interesting about the respiratory mechanics. For spending some time with us. Hopefully that was a little informative, and we'll see you soon in other lectures.